Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be covering a couple of applications of derivatives, specifically derivatives as a rate of change, although we are going to be doing a lot more applications of derivatives in the rest of this course. So we're going to start with a few of the simple ones. One of the major application of just pure derivatives is in one-dimensional motion or motion along a line. So the rate of change of position or displacement with respect to time is called velocity. And it sounds like a rate of change because it is. And we've already covered average velocity. So the average velocity on a time interval from A to B, if you are given a position function s of t, is going to be s of b minus s of a over b minus a. And that is average velocity between two distinct points in time. Now, instantaneous velocity is something that we've already touched on. Instantaneous velocity was the slope of the tangent line of the position function at the point A. And the instantaneous velocity is given by this formula, which looks like the definition of the derivative because it is. So basically, velocity is the derivative of position. So the velocity function is the derivative of the position function. So let's say that for this graph here, this graph models a path of a police patrol car. So let's say that a police station is located along a straight east to west freeway. At noon, which is defined as t equals 0, the patrol car leaves the station and heads east. And the position function of the car, s equals f of t, gives the location of the car, where miles east counts as positive positions and miles west counts as negative positions. And it gives the position of the car a number of miles from the station at time t equals whatever hours afternoon. So t is the number of hours afternoon. So what we're going to do is we're going to just kind of describe the location of the patrol car during this first 3.5 hours. So from here to here. So at t equals 0, which is noon, the car starts heading east, and it is east because this is a positive position. Positive positions were defined as miles east. Until about 1:15-ish. And then from about 1:15 to a little after 2 o'clock, it looks like the patrol car was at rest, demonstrated by this constant here. And then after about 2 o'clock, the car starts to then head west because this is a decreasing position. Decreasing position means that the position is growing more and more negative, which means that the car is heading back west. Then the car gets back to the station at around 3:15, and then after 3:15, so from 3:15 to 3:30, the car continues to head west, which is why the position function dips below the t-axis, indicates that he is now west of the police station. So what we're going to do is we're going to calculate the average velocity of the car between noon and 2 p.m. So between noon and 2, noon is time t equals 0, and 2 p.m. is time t equals 2. So we're calculating the average velocity between noon and 2. Now remember, average velocity is the slope of the secant line between the 2 points. So the average velocity would be the slope of the secant line between noon and 2. So we're going to take the ending position, which is going to be s of 2, minus the starting position, which is s of 0, divided by the length of the time interval, so the ending time 2 minus the starting time 0. So s of 2, which is 80, minus s of 0, which is 0, over 2 minus 0, gives us an average velocity of 40, and this is going to be in miles per hour. So that means on average for these first 2 hours of the trip, he was traveling at an average of 40 miles per hour. So then what we're going to do is we're then going to calculate the average velocity of the car between 2 p.m. and 3 p.m. and we're going to use that to describe its displacement. So remember, average velocity depends on you having 2 distinct points in time. This time it is between 2, which is t equals 2, and 3:30, which is t equals 3.5. So the average velocity between 2 p.m. and that's a terrible line, but you get the idea. It's the slope of the secant line between 2 and 3.5. So we're going to find the slope of that line by taking the ending position, which is s of 3.5, minus the starting position, s of 2, divided by the ending time, 3.5, minus the starting time, 2. So then you're going to get, s of 3.5 minus s of 2 is actually negative 100, divided by 1.5, gives you approximately an average velocity of negative 66.7, and this is going to be in miles per hour. So why was velocity negative? Remember, velocity is the change in displacement over the change in time. Time is never negative, so in order for velocity to be negative, displacement needs to be negative. Remember, pure velocity gives not only speed, but it also gives direction. So it tells you how fast they are going and in what direction. And the negative velocity here indicates that he is heading west, because west is defined as negative position. So this means that on average, between 2 and 3:30 p.m., he was heading west at about 66.7 miles per hour. And then for part D, at what time is the patrol car at rest? It looks like between around 1:15 and 2. Now, speed and velocity are related to each other, but they are different. Velocity is the change in displacement over time. So because, as we saw in the last example, displacement can be negative, velocity can also be negative. Speed is just a magnitude. Speed just measures how fast. How fast is the car going? And speed does not care about direction. It's just asking how fast is this object traveling regardless of direction. So speed is always positive. So speed is the absolute value of velocity. So speed can be thought of as the absolute value of velocity, or you can also think of speed as the absolute value of the derivative of position. So then acceleration is the rate of change in velocity with respect to time. Now velocity itself is a rate of change. So you are finding the rate of change of the rate of change. So because acceleration is the rate of change of velocity, acceleration is the derivative of velocity. And since velocity itself was already a rate of change, velocity can also be thought of as the second derivative of position. So acceleration is either the first derivative of velocity or the second derivative of position. Now remember, because velocity can be negative, acceleration can also be negative. So this is just a slide that kind of sums it all up. If you are given a position function s, the velocity is the derivative of the position function. Speed is the absolute value of velocity, and acceleration is the derivative of velocity or the second derivative of position. So let's suppose that the position, which is measured in feet, of an object moving horizontally in time t seconds is s equals t squared minus 5t, and t is defined between 0 seconds and 5 seconds. And so this object is moving in a horizontal line, so it's moving left and right and back and forth, and it's got this position function t squared minus 5t. And we're going to assume that positive values of s correspond to positions to the right of s equals 0. So positive is defined as movements right, negative is defined as movements left. So what we're going to do is we are going to find and graph the velocity function on the time interval 0 to 5, determine when the object is stationary, moving left, and moving right. So let's first find the velocity function. The velocity function is going to be the derivative of position. So the velocity function is going to be the derivative of t squared minus 5t, so the velocity function is going to be 2t minus 5. 2t minus 5, you can graph that. That is a line with a y-intercept of negative 5 and a slope of 2, so it looks something like this. And remember, this is the graph of the velocity function. When velocity is negative, that means the displacement was negative. When velocity was positive, that means the displacement was positive. So clearly, the velocity function is below the x-axis, or t-axis, at some points, and then above the t-axis at others. And it crosses the t-axis at one single point, and we know that because this is a linear function. So let's first find where that velocity function crosses the t-axis. So we're going to set velocity equal to 0, and we're going to solve for t. So when we solve for t, we get t equals 5/2. Now when the velocity is 0, that means that the object is stationary. A 0 velocity means that the object is not moving. So t equals 5/2 is when the object is stationary. And since this is the only point where the velocity function is equal to 0, that means that the object needs to be moving either left or right for the rest of the graph. So right there, that is 5/2. So the object from 0 to 5/2, the velocity function is below the x-axis, so that means the object is moving left. So the object is moving left. From t equals 0 to t equals 5/2. It is stationary at 5/2. So stationary at 2.5 seconds. And then after 5/2 seconds, so after 2.5 seconds, from 2.5 seconds to 5 seconds, the velocity function is above the x-axis. So because the velocity is positive, that means displacement is positive. Positive is defined as movements right. So then the object is moving right from t equals 5/2 to 5. Now for part B, we're going to find and graph the acceleration function on the interval 0 to 5. So acceleration is going to be the derivative of velocity, also known as the second derivative of position. So the derivative of the velocity function is 2. So that means that the acceleration function is actually a constant. The acceleration is constant from 0 to 5, and its graph looks something like this. Now for this next one, let's say that a stone is thrown vertically upward with an initial velocity of 64 feet per second from an initial height of 90 on a bridge of 96 feet above a river. By Newton's law of motion, the position function, which is measured in the height above the river after t seconds, is given by this function s of t, where s equals 0 is the surface of the water. So then, we're going to, for part A, we're going to find the acceleration and velocity functions. So we're going to start with velocity. So the velocity function is the derivative of the position function, the first derivative of the position function. So the first derivative of the position function is actually going to be negative 32t plus 64 after a little bit of power roll. Then the acceleration function, acceleration is the derivative of velocity, so the derivative of the velocity function is this negative 32, which if you have taken physics before or if you have had any exposure to physics, this is the acceleration due to gravity in feet per second squared. So then for part B, we're going to find the highest point above the river that is reached by the stone, and we're going to use calculus to find this. I know that you can find this algebraically. We are not going to be doing that. This is a calculus course, so we're going to be using calculus to find the maximum height of the stone above the river. So the stone's path is going to look something like this. It is tossed around 96 feet. It goes upward, has a maximum height, and then it curves back down, and then it hits the water at some point. Now this maximum right here, the maximum height of the stone, if you think in terms of tangent lines, what is the slope of the tangent line at this maximum? Well, we covered this back in way earlier in chapter 3. The tangent line at this maximum height is actually 0. So because the slope of the tangent line is 0, that means that the derivative is equal to 0. So if this graph here models the position function, the derivative of position at this point is going to equal 0. Derivative of position is also known as velocity. So the object will be momentarily stationary at its maximum height, which means it will have a velocity of 0 at its maximum height. So what I'm going to do is I am going to set the first derivative of position, which is also known as velocity. I'm going to set it equal to 0, and I'm going to solve for t. So when you solve for t, you're actually going to get t equals 2. Now, this is actually when the stone reaches its maximum height. That is not the actual maximum height. To find the actual highest point or the actual maximum height, what you're going to do is you're going to take this 2 and you're going to plug it into the position function into everywhere that you see a t, and then that will give you the actual maximum height. So 2 is when the maximum height is reached. To find the maximum height, you're just going to find s of 2, and s of 2 is equal to 160 feet. So the stone's maximum height is 160 feet. So then for part C, with what speed will the stone strike the river? So remember, s equals 0 is the surface of the waters. S equals 0 is right there. So we first need to find when the stone strikes the river. So to find when the stone strikes the river, we're going to take the position function and we're going to set it equal to 0. And you can either use a quadratic formula or you can use a graphing calculator. You can ignore the negative t-intercept and you're just looking at the positive t-intercept. So with either quadratic formula or a graphing calculator, you get 5.16 as the time when the stone strikes the river. To find the speed at which the stone strikes the river, we need to do a little bit more than this. So 5.16 is the time that the stone strikes the river. Now remember, speed is the absolute value of the velocity function. So what we're going to do is we are going to evaluate the velocity function at 5.16 seconds. Then we're going to take that number and we're going to find its absolute value. So if you plug 5.16 into the velocity function, you get negative 101.1. However, speed is just a measure of how fast, and speed does not care about distance. So the absolute value is 101.1, and this is going to be in feet per second. Remember, speed is just a magnitude of how fast. Speed is always positive because it does not care about direction. Velocity takes direction into account. Now, one-dimensional motion is not the only applications of derivatives. Any quantity that is changing, you can model the rate of change as a derivative. So the derivative of any function that is actively changing will give you the rate of change of that function. So let's say that you have some sort of quantity f of t which is growing. I don't care what it is, what it could stand for. Let's just say f of t models a function that is a growing quantity. So the average growth rate is just going to be the average rate of change of the function f of t on the time interval a to b. So the average growth rate is going to be the ending value f of b minus the starting value f of a divided by the time interval b minus a. Now the instantaneous growth rate is the derivative of the growth function. So if you want to find the instantaneous growth rate of a growth function, all you have to do is take the first derivative and evaluate it at the time in question. So let's say that the number of internet users from 1995 to 2010 is modeled by this function p of t, where t measures the number of years after 1995. So obviously this is a growth rate because the number of internet users is growing, and we can see that by the quadratic function with a positive leading coefficient. This is clearly a growth rate. So what we're going to find is the average growth rate from 2000 to 2005. So since t is the number of years after 1995, the year 2000 is a t-value of 5, and the year 2005 is a t-value of 10. So to find the average growth rate, that is going to be the slope of the secant line of this function between t equals 5 and t equals 10. So the average growth rate is going to be p of 10 minus p of 5, so the ending value minus the starting value, divided by the length of the time interval, so the ending time 10 minus the starting time 5. So if you evaluate p of 10, you get 962. Minus p of 5 is 383, all divided by 10 minus 5, and you're going to get approximately 116. And the units for this are going to be in millions of users per year. Sorry I didn't indicate that p of t was measured in millions of users. It's measured in millions of users. So the average growth rate, so on average between 2000 and 2005, the number of users grew at an average rate of 116 million users per year. Now remember, that is just the average growth rate. The instantaneous growth rate at any given one single year might be different. So we're going to find the instantaneous growth rate in 2006. So 2006 is 11 years after 1995, so t equals 11. So what you're going to do for instantaneous growth rate, that is also known as a derivative. The derivative is an instantaneous rate of change. So if you take the first derivative and evaluate it at 11, you are going to get the instantaneous growth rate in the year 2006. Now you can very easily do this by hand by taking the derivative and then plugging in 11, or there is also a way to do this on a graphing calculator. I can't show you the graphing calculator steps because if I try to open another program while this is running, it will crash my PC. My PC is not great. So I did record a video on how to find a numeric derivative on a graphing calculator, and I will leave a link to that video in the description. So go check that out, and these are very valuable steps. You can use a calculator to find a numeric derivative. But anyway, whether by hand or on a graphing calculator, you will get a p prime of 11 of approximately 137, and this is going to be in millions of users per year. And because the derivative is positive, that means that this is a rate of growth. So what this means is that in the year 2006, the number of internet users was increasing at a rate of 137 million users per year. Now, the whole point of growth models is to predict values that are not in the given time interval. So what we're going to do is we're going to use this model to predict the number of internet users in 2015. 2015 is a t-value of 20. So if you predict, if you want to predict the number of internet users at t equals 20, all you have to do is plug 20 into p, and you get 2,570 million users, and that is going to be your predicted value. Now, there are a whole bunch of applications of just first derivatives. We're only covering a few of them. The major courses that in your programs that require calculus are going to go into way more applications of derivatives. So your major courses will get really specific on how calculus and derivatives are applied to your specific degree program. We're just doing a whole bunch of the common ones in this class. So another application of derivatives is in business and economics. So if you have a cost function c of t, the cost function c of x gives the cost that is required to produce x number of items. So you also have what is called average cost and marginal cost. So the average cost is exactly what it sounds like. It is the cost on average to produce X number of items. Now, average cost, you read this first part as C bar of X. This bar that's here on the top of the C, this is just a very common way of indicating an average. You see this a lot in statistics. So C bar of X is just the average cost. So the average cost function is given by the cost function c of x divided by the number of items x that were produced. Now, the average cost per item to produce delta x additional items is called the marginal cost. So the marginal cost is the average cost to produce delta x additional items after x. When we actually do an example, I think that will make more sense. But the marginal cost is given by the first derivative of the cost function c prime of x. So let's say that the cost of producing x number of items is given by this function c of x, and it is defined between 0 and 1,000. So what we're going to do is we're going to find the average cost function and the marginal cost function. So the average cost, which is c bar of x, is going to be the cost function c of x divided by x. So I'm just going to take every single term in the cost function and I'm going to divide them all by x. So we will get negative 0.02 x plus 50x divided by x is 50 plus 100 over x. So there is your average cost function. We're also going to find the marginal cost function. So marginal cost is the derivative of the cost function. So the marginal cost is actually negative 0.04x plus 50. So for part B, what we're going to do is we're going to use those functions to find the average and marginal cost when x equals 100 items, and we're going to interpret those values. So let's start with average cost. So c bar of 100. We're going to plug 100 into the average cost function, and we get approximately 49. So what this means is that it costs, on average, if you have 100 items, it costs on average $49 an item to make them. So for the first 100 items, it costs $49 an item on average. Now the marginal cost, if you were to plug in 100 into the marginal cost, you are going to get $46 per item. So what this means with the two of them together is that the cost of producing 100 items averages out to costing approximately $49 each. However, after the 101st item, the average cost is going to go down to only $46 per item. So producing that one extra item means that producing them is less expensive. So the average cost for the first 100 items is $49 per item. But after the 101st item, the average cost will go down to $46 per item. So what we're going to do is we're going to do that again when x equals 900, and we're going to interpret those values. So we're going to find the average cost for 900 items. So we're going to find c bar of 900. And we're going to find the marginal cost c prime of 900. So plugging 900 into the average cost function, we get approximately $32 per item. And then plugging 900 into the derivative, or the marginal cost, you're going to get $14 per item. So what this means is that the cost of producing the first 900 items is approximately $32 per item. But after the 901st item, the average cost drops to $14 per item. So this is the marginal cost is why mass producing means that you can produce things cheaper up to a point. All right, so that is it for this section of applications of derivatives. Like I said, we're going to be doing a lot more of these in the course as you learn more and more derivative rules. But at this point, you could learn at least a few of the basic ones representing derivatives as a rate of change and being able to apply those to specific contexts. So we're going to spend the next few sections going over some more derivative rules. So make sure that you tune in for those videos. So thank you all very much for watching, and I will see you guys in the next video. Bye-bye.